it gets hard by Saturday. And
Right.
then the magazine section in the New York Times has a different, has a variation also.
Right,
I
well, the
love
crosswords
campaign.
are like that too.
Yeah.
Monday is easy and Saturdays are hard. All right, let's resume. We got a lot to cover here.
Yeah.
Question?
On your kitty cat stuff, there's a book, I Contain Multitudes by Ed Young, which talks about the multitudes of bacteria within us and their interplay and the kind of stuff that you were talking about with cats. And it has the same kind of detail in a way that you're talking about here within the cosmos. And it's an incredibly interesting book, and one of the things that I remember is that his comment is, we contain more bacteria within us than there are stars in the sky.
Right.
Yeah. It's
This
a
I've
big
heard.
book.
Yes, sir.
Would you want to mention Isaac Newton's spinning bucket?
Oh, yeah.
Your first lecture, you said, we know how fast galaxies rotate, which means we can measure their movement. If you take a top and you spin it, it will stand up. If I take my top that's spinning from my galaxy and Steve leads his galaxy with his top spinning and we meet somewhere in the middle, do we both understand what zero spinning is? Do our tops lay down at the same time, stand up, and we
Now,
appear to be-
so Michael and I have been in a correspondence about the issue of how do you know when things are rotating in the universe? This is a very intriguing question, and Newton's bucket is something you could look up, and he just mentioned it. And Newton's bucket is this idea: if you have a bucket of water and a rope, and you twist the bucket, energy, you can store some energy in that rope, and when you let it go, the bucket will spin. As it's spinning, the water will crawl up the sides a little bit. You have like a concave surface. But another individual who's watching this experiment, or doesn't know how you did the experiment, but they're orbiting around at the same rate that the bucket is rotating. They just look at the bucket and it's just standing there. It's like a carousel that's not moving. They are not going to see water go up. They'll see a flat surface. And this is a question that Newton started, and it's intimately involved in the concept of how space and time are connected. And Newton understood this is a dilemma. Who's right? Particularly if you do the experiment out in space and there's nothing else around to provide a reference. How would you know, for example, that you are not rotating? If you go out in empty space and there's no stars to observe and you're just there, you're having lunch and whatnot, how do you know you're not rotating? That is, if you were, would you feel an acceleration if you were rotating quickly? Like we all, you've seen ice skaters and they can control their spin rate by moving their arms out in and out. Would you have that experience in an empty universe? Nobody knows. People argue about this all the time. And, yes?
In your bucket thing, if the bucket were rotating on Earth where we have gravity, and somebody were on the bucket rotating, they would still see the water rise because
That's
of the
true.
effect of gravity.
Right,
It's only an empty space that they might not.
right. They can tell.
Yeah, I read once where if you were riding in an elevator and the elevator were accelerating, you would think you had gravity.
Exactly. This is
You wouldn't
Newton's,
know.
this is Einstein's big insight when he was struggling with his equations of gravity. The whole thing became simple for him when he realized that a person in a gravitational field, falling in a gravitational field, and a person out in space away from any gravitational influence, they are having the same experience. astronaut, so if you're in the elevator and somebody cuts the cord, you and the elevator box and everything in the elevator accelerates at the same rate. You can't tell that you're accelerating near a gravitational body. You have exactly the same experience you would have if you were in a box out in deep space with nothing around, with one exception, and that is the tidal force. So if you are in the elevator here in this building, you have two oranges, and somebody cuts the cord and you release the oranges are going to fall with you, and you would say, I might be in deep space. Everything is, like you see this all the time, the astronauts the pen is floating in front of them. The orange would be floating there, but the acceleration that the two oranges feel is not exactly the same, because both oranges are falling toward the center of the planet. So there's a small effect causing the oranges to go this way, because the two oranges are falling on radii.
That's right.
So you would see, so this is where Einstein used his fantastic intuition. He said, as long as the volume of space I'm talking about is small, the tidal force is not observable. And this helped him conceptualize what he and Grossman eventually wrote down. If you're in a small space, the two oranges, like if you're falling in an elevator in this building, you'll never detect the fact that the oranges are moving together. If you're near a black hole, you will feel it, because everything gets crushed this way, and then because gravity at your feet is stronger than gravity at your head, you get stretched and you get spaghetti. So, but the empty space water bucket is very intriguing.
If, the core issue I was looking for was, is there a universal state of zero angular momentum? Now, if there is not a universal state of angular momentum, then my observation of galaxy X from my galaxy, and Steve's observation of galaxy X from his observation point, our measurements are not consistent.
Right.
And so, if there is no such thing as universal zero angular momentum, then all our measurements of rotation and Doppler shift and redshift are unique to us, but not unique across the universe.
Yeah, and there's a small community of cosmologists who focus on these questions of the impact of geometry on observational accuracy. And it doesn't seem to be a problem with the current technology we have for looking at galaxies and space. We measure rotations, we look at spectra from the galaxies, that's how we detect the rotation. It all seems to make sense right now, but it could be that the effect you're describing is so small that it's not an issue yet. And we're going to see that here in a second, because we're going to talk about the Hubble constant. So we've already really talked about this. Why is the dark energy per unit volume, why is it so small? Way, way smaller than you'd expect. Here's some of the math that I teach. So this is Casimir, who predicted that you could go in the lab and measure the energy density in a vacuum. And famous scientists, this is the late 40s, what famous scientists said, this guy is nuts. Here's what he said. He said, if I take two plates and I put them very close together, there will be a force between the plates. Why is that? Because if empty volume is a boiling, churning foam of particles that come into and leave existence, influenced by the laws of quantum mechanics, just stuff popping up and disappearing on very short time scales. But this churning is going on. Now, if I put my two plates in there, and I put them really close together, the bigger particles, or the stuff that's popping into and leaving existence, the bigger stuff can't fit between the plates. So what's between the plates is only the small stuff. But around the two plates, all sizes of virtual particles are being created and destroyed at a rapid rate. So in the box, there's energy churning around, but between the two plates, the same energy exists minus the big stuff. So it's like squeezing on a balloon. We should measure, the two plates should be forced together. And people thought he was nuts. And he was a contemporary of Freeman Dyson and the guys who were working on quantum electrodynamics, the same techniques involving throwing away infinities. Yes, sir?
Well, couldn't it be the atomic forces of the atoms in the two plates attracting each other?
Right, so you have to, if you're going to do the experiment, you have to make sure you don't let that happen. You have to, the plates have to be very close together, but not so close that the atoms of this plate and the atoms of this plate are interacting. No electrostatic things. Okay, so this is an experimental challenge. So Casimir said, energy, there should be energy in empty space. We should measure it. It should be measurable by measuring the force between the two plates. And in the late 1980s, the measurement was finally made. I'll show you it in a second. And they confirmed his calculation, which is a great achievement. There's a picture of the two plates being forced together. And I want to show you a little video. This is the video. So there, floating are two pieces of wood floating in water. And under this sink are vibrators that are going to create a bunch of waves. And there's some strings there just to hold the sticks, to suspend them on the water. Not sure why. But see what's happening here? The waves here in the middle, the big waves can't fit. But there are big waves out here. And the two sticks get forced together. That's the idea of the Casimir effect. And here's the theory. And the experiments are the little squares and circles. The measurement is the dotted line, and then they correct for what Ansel just brought up, the electrostatic force between the atoms of the two plates. If you correct for that, the theory and the measurements match. Okay, so Casimir, genius work. Good job. Now, if we use his number for vacuum energy, the calculation he did, and apply it to the universe as a whole, it's wrong by a factor of 10 to the 120th. It's the worst prediction in the history of science. Not Casimir's fault, but damn it, doesn't explain dark energy. So I want to cover some more topics because I just talked too much today. Hubble, big trouble with Hubble. I may have shown this before. So there are people using variable stars to measure the Hubble constant. So let's clear up some language here. Everybody calls it the Hubble constant. It's the expansion, the number that describes the expansion rate. It's not a constant. The Hubble constant changes as the universe evolves. It was very different in the early universe, much, much higher. It's the Hubble number is probably better language. But here's the problem. Cepheid variable, okay, so we're talking about the last 20 years of science. 20 years ago, the uncertainty about the estimate of the Hubble constant this was the average, around 72 with this error bar. And separately, people were looking at the cosmic microwave background data because from that you can get the expansion rate of the current expansion rate of the universe. And they had a number very close to the same with an error bar. And we'll leave this for, I'll talk about that in a second. Over time, everybody was content that we're just got to make the measurements more refined. And they did. And here's the problem now. Starting in 2012 or so, people noticed, wait a minute, the variable star measurements are going up toward a number like 74, and the microwave background is now at about 68. And because the measurements are so much better now, we can see these things don't agree. So then somebody, once again, a lady astronomer, came up with this thing. This is this red giant, that RGB means red giant branch. She came up with an independent technique, and unfortunately, it's right in the middle. Now, yesterday, there was new stuff popped up, which has to do with a new result from gravitational lensing of quasars. They get 73, which puts it in this bucket. And holy cow, which measures something very interesting I'll describe in the next chart, they also get a 73 number. The cosmic microwave background number is not playing well with others. We don't know why. The possible reason, which is very intriguing, is the evolution of the universe that we see. Let's back up. The cosmic microwave background is a picture of light as it was right after the universe became transparent. So it's 400,000 years after the Big Bang. So it's a picture of the very early universe, and there's this expectation about how the universe evolves that leads to this number for cosmic microwave background, and it appears there's something about the evolution of the universe we do not understand. That it's a real problem. It's a real problem for Adam Rice too, who got he and two others got a Nobel Prize for this result. So right now we have a major issue. It's like the #1 problem in astrophysics cosmology. What's going on with the Hubble number? And this is good because there's something about the evolution of the universe since the picture was created that we do not understand. There may have been an interval, for example, when the expansion rate was dramatically different than the data imply. Just an unresolved issue. But it was not seen until 2012, when the data got cleaner. So the intriguing thing is this. This is new results as of maybe 2 or 3 days ago. This is called strong lensing. Here's, let me show you. Oh, here it is. I think we're going to watch a little video clip. No, sorry. That's somewhere in here there's a link. Here it is. So let me tell you what you're going to see, because the video only lasts about 20 seconds. If you're looking at a distant object, it has to be bright or you wouldn't see it. And a quasar, which is the accretion disk of a gigantic black hole, is really bright. So we see these quasi-stellar objects called quasars, only because they emit an enormous amount of energy and they're far away. The light propagating to us then its trajectory gets altered by the mass that is in between the source and our telescopes. Because that mass, that energy, bends the path of the light. Depending on the path the light takes, there's a time difference in how long it takes the light to get to us. And that time difference is measured on a scale of weeks. So this is, today it seems to be the Woman Astronomer Day. This is also work done by a woman astrophysicist. She figured out that she was able to make measurements of the time delay for different paths from a single quasar. So you see, important, you see multiple images of the quasar because of the light path getting distorted. The trajectory gets changed. So you see a number of different patches of brightness on the sky. When you look at this quasar, you can identify them as all being from the same source using the Doppler shift, the rate at which this object is going away from you, and the spectra. So you can look at the content of the quasar, the chemistry of it, and how fast it's receding. You say, hey, all these things are the same thing. It's just different different images of the same thing. And the light is arriving at different times because the path lengths are different. This is pretty intriguing. The path lengths are different on a scale of weeks. From this, and so here's what she's got. She's got, and here's the last 20 years roughly. These are what are called light curves. She's looking at the quasar's light intensity changing. These are all of the same object, 4 different images, A, B, C, and D. And if you expanded this and looked at detail, you would see the event structure is delayed. That delay tells you something about the size of the universe. Size of the universe tells you about the expansion rate. So she's been doing this for almost now 20 years, and her results are right here. She's getting 73.8. It's a technique that was predicted back in the 60s, but technology didn't exist then. And this gal, you can look it up, or you can read this little article. She can actually see the time delay, the path difference, and gets a number, and notice this, she's getting a number to 3 decimal places. It's a really good technique, but it does not stand next to the cosmic microwave background version. Something is not good. So this is more detailed. Dark matter. We only know we're about 5% of the stuff in the universe in terms of stuff being energy or matter. What is going on with dark matter? We think we understand. I'm just going to slide through these. I've shown most of this before. This is actually a picture of the distribution of dark matter derived from looking at lensing, that is, images being distorted by mass. And it's stuff floating around. Nobody knows what it is. It has a gravitational influence, but it doesn't produce or interact with light. So we can't identify it. Here's some, once again, here's some possibilities. One brand new one popped up. So, to talk about the new idea of what dark matter could be, we have to go back to a chart I showed you almost 2 months ago, and that is the quark world. So there's this collection of subatomic particles that works extremely well. This is called the standard model of particle physics. And with it you can predict all kinds of temporary particles that will be made in an accelerator like the one at CERN. It really works. Everything makes sense. What's intriguing about it is it was discovered in the late 60s, early 70s, that all the stuff we're made of is made up of these things. These are quarks. The up, charm, top, down, strange, and bottom quarks. They have these funky names. And if you put 3 of these particles together, you make something that's part of our world. These quark objects do not exist in our universe standing alone. They existed in the early universe because the energy levels were so high that an electron got ripped into its quark components, or a proton got ripped into its quark components. These days, you can make quarks temporarily in an accelerator. That's the only place they exist. So, quarks can be used to build stuff. I'll give you an example right here. 2 ups and a down. Here is the ups and downs are these guys. 2 ups and a down, you have a proton. 2 downs and an up, you have a neutron, and so forth. This is genius work by Murray Gell-Mann. He won a Nobel Prize for figuring this all out. And Murray Gell-Mann, by the way, just died 6 months ago, wrote a number of books for the general public who are interested in these topics. So, that's our refresher on quarks. Particles that you are gathered together in groups of 3 to form the components that exist in the nucleus of atoms, without which we would not exist.